You look up at the night sky, you see stars, maybe a planet or two. If you are far from city lights, you might see a faint milky band stretching across the darkness. That's our galaxy, the Milky Way. It feels huge, it feels like everything, and for most of human history, it was. We thought the entire universe was contained within that band of light. Then we learned better. We learned those faint smudges of light were other galaxies, just like our own. Islands of stars, each containing billions of suns. Our universe got bigger. We found out our Milky Way wasn't alone. It was part of a small group of galaxies, the local group. Andromeda is our biggest neighbor, hurtling toward us for a future collision. This was our little cosmic neighborhood. Then the map expanded again. We saw that our local group was just one small part of an even bigger collection of galaxies. This was the Virgo Supercluster. It was a sprawling, messy collection of thousands of galaxies centered on the massive Virgo cluster. For decades, this was our address. We lived in the Milky Way, in the local group, on the outskirts of the Virgo Supercluster. It felt like we finally had a handle on our place in the cosmos. But there was a problem. The map was fuzzy. The edges of the Virgo Supercluster were not clear. It was defined by just looking at where galaxies were clustered together. It was like trying to define a country by looking at a nighttime satellite photo of its cities. You can see the bright spots, but where do the borders actually lie? Where does one country's influence end and another's begin? Scientists knew there had to be a better way, a way based not just on where things are, but on the underlying forces that shape them. That's where the story of Laniakea begins. It's the story of a new map, a map that redefined our home and showed us that we are part of something far grander and far stranger than we ever imagined. Before we can understand Laniakea, we have to understand the old way of thinking. For a long time, astronomers mapped the universe like they were charting islands in an ocean. They looked for clumps of galaxies. They saw our Milky Way and Andromeda were the two big players in a small club called the Local Group, with a few dozen smaller galaxies orbiting us. It was a cozy, gravitationally bound family. We're all stuck together. Then, looking further out, they saw the Virgo cluster. This is a real beast. It has over 1,000 galaxies packed into a relatively small space. It's the nearest massive galaxy cluster to us, and its gravity is powerful. The Virgo cluster pulls on everything around it, including our own local group. We are moving toward it. So it seemed logical to draw a big circle around the Virgo cluster and all the little groups like ours that seem to be associated with it. They called this the Virgo Supercluster. This was our home for a long time. It was about 110 million light years across. It was a significant piece of the universe, but the definition was loose. It was basically a list of galaxy clusters that seemed to be in the same general area. There was no clear boundary. Is that galaxy over there part of our supercluster or the next one over? It was hard to say. It was a bit like looking at a crowd of people and trying to draw lines around different groups of friends. Some groups are obvious, but at the edges people are just mingling. The key issue was gravity. Gravity is the architect of the universe. It pulls matter together. On the largest scales, the universe is expanding. Everything is, on average, moving away from everything else. This is called the Hubble flow. You can think of it like a loaf of raisin bread baking in an oven. As the dough expands, every raisin moves away from every other raisin. But gravity fights this expansion. In places where there is a lot of matter packed together, like in a galaxy cluster, gravity wins. The galaxies in the cluster are bound to each other. They orbit a common center of gravity and don't expand away from each other. The local group is bound. The Virgo cluster is bound. But what about the supercluster? Was the Virgo supercluster a single gravitationally bound object? The answer seemed to be no. The expansion of the universe was stronger than the overall gravity of the supercluster. The different groups within it were, on average, still moving away from each other, even as they were all being tugged toward the central Virgo cluster. So the old map was a bit of a mess. It was a good first attempt, but it didn't capture the underlying dynamics of what was really happening. It didn't tell the full story of gravity's influence. Scientists needed a new way to define these massive structures. They needed a definition based on movement, a definition based on which way the cosmic rivers were flowing. In 2014, a team of astronomers led by R. Brent Tully at the University of Hawaii changed everything. They published a paper that drew a new map of our local universe. They gave our home a new name, Laniakea. Their idea was simple in concept, but incredibly difficult in practice. Instead of just looking at where galaxies are, they decided to look at where galaxies are going. They focused on a galaxy's peculiar velocity. This sounds complicated, but the idea is straightforward. Imagine You're on a moving walkway at an airport. The walkway itself is moving forward at a steady speed. That's the Hubble flow, the expansion of the universe. Now, you start walking on the walkway. Your own walking speed is your peculiar velocity. It's your motion relative to the walkway itself. You might be walking forward faster than the walkway, or you might turn around and walk backward against the flow. Galaxies do the same thing. The expansion of space carries them apart, but local gravity pulls on them, giving them their own peculiar velocities. A galaxy might be pulled toward a massive neighbor, adding to its speed, or it might be pulled back toward a dense region it's moving away from, slowing it down. These tiny deviations from the pure expansion of the universe are the fingerprints of gravity at work. Tully's team spent years building a massive catalog of these peculiar velocities. They measured the speeds of over 8,000 galaxies in our cosmic neighborhood. This was a monumental task. You can't just point a telescope at a galaxy and see how fast it's moving toward or away from you. You have to use clever tricks like measuring the brightness of certain types of stars or the rotation speed of the galaxy itself. These methods allow you to estimate the galaxy's true distance. Once you know its distance, you can calculate how fast it should be moving away from us due to cosmic expansion. Then you measure how fast it's actually moving. The difference between those two numbers is its peculiar velocity. It's the extra push or pull from local gravity. With this huge database of motion, they could finally see the big picture. They could trace the paths of galaxies. They saw streams and rivers of galaxies all flowing in the same direction. And they realized they could define a supercluster in a completely new way. They borrowed an idea from geography, a watershed. On Earth, a watershed or a drainage basin is an area of land where all the water that falls there drains into a single river, lake, or ocean. There are high ridges that separate one watershed from another. A drop of rain that falls on one side of the ridge flows to one ocean, while a drop that falls a few inches away on the other side flows to a completely different ocean. Tully's team applied this concept to the cosmos. They defined a supercluster as a cosmic watershed for gravity. A supercluster is a region of space where all the galaxies are flowing toward a single common center of gravity. The boundary of the supercluster is the line where the flow divides. On one side of the line, galaxies flow toward our basin. On the other side, they flow away toward a different basin. When they applied this new definition, the old map of the Virgo Supercluster dissolved. It turned out that the structure we called the Virgo Supercluster was just one small part of a much, much larger system. This new system, this immense gravitational basin we call home, is Laniakea. The name itself is beautiful. It was suggested by a Hawaiian language professor at the university. Lani means heaven, and Akea means spacious or immeasurable. Laniakea, immeasurable heaven. It's a fitting name for the sheer scale of our home. So what is Laniakea really? Let's talk about the scale, because it is almost impossible to comprehend. Laniakea is about 520 million light years across. A light year is the distance. Light travels in a year, which is about 6 trillion miles. So 520 million of those. Our own Milky Way galaxy is about 100,000 light years across. If the Milky Way were the size of a grain of sand, Laniakea would be the size of a large football stadium. It is absolutely immense. Within this vast structure, there are an estimated 100,000 galaxies, similar in size to our own Milky Way, plus countless smaller dwarf galaxies. The total mass of all the stars, gas, dust, and dark matter within Laniakea is staggering. It's about 100 quadrillion times the mass of our sun. That's a 1 with 17 zeros after it. But here's the most important and perhaps confusing thing about Laniakea. It is not a single solid object. It is not a country with firm borders. It is a region of influence defined by motion. And critically, it is not gravitationally bound. This is a key point. A structure is gravitationally bound if its own internal gravity is strong enough to overcome the expansion of the universe. Our solar system is bound. The planets will keep orbiting the sun. The Milky Way galaxy is bound. Its stars will keep orbiting the galactic center. Our local group, with the Milky Way Andromeda, is bound. We will eventually merge. Even the Great Virgo Cluster, at the heart of our old supercluster, is mostly bound. Laniakea is not. The pull of all its 100 quadrillion suns worth of mass is not enough to stop the cosmic expansion across its vast expanse. The dark energy that drives the expansion of the universe is winning. This means that most of the galaxies inside Laniakea are still moving away from each other. They are just moving away from each other more slowly than they would be if Laniakea's mass wasn't there. Think of it like a group of people on a giant, slowly expanding rubber sheet. Everyone is moving apart as the sheet stretches. But imagine, there's a slight dip in the sheet. People near that dip will slide toward its center, even as the sheet itself continues to expand. Their movement apart is slowed down, or even reversed in the very center. Laniakea is that dip. It's a region where gravity is putting up a fight against expansion, but ultimately it's a fight it will lose. This means Laniakea is a temporary structure. It exists now, a snapshot in cosmic time. In the distant future, as dark energy continues to accelerate the expansion of the universe, the connections that define Laniakea will be broken. The great rivers of galaxies will dry up. The different clusters and groups within Laniakea will eventually be pulled so far apart that they will lose sight of each other forever. Laniakea will dissolve back into the expanding cosmos. So where are we in this immense flowing structure? We are not in the center. We are not in a prominent place. We, in our Milky Way galaxy, are located on the very outskirts of Laniakea. We are in one of its distant provinces, a small tendril of galaxies far from the bustling core. The center of Laniakea, the point that everything is flowing toward, is a region of space known as the Great Attractor. This is the bottom of our gravitational basin. The Great Attractor has been a mystery for astronomers for decades. Long before Laniakea was defined, they noticed something was wrong with the motion of our galaxy and our neighbors. There was a huge, unseen mass out there pulling us and thousands of other galaxies toward it at a speed of hundreds of kilometers per second. The problem was we couldn't see what it was. The Great Attractor lies in a direction that is blocked from our view by the plane of our own Milky Way galaxy. This is called the zone of avoidance. Our galaxy is a flat disk, and it's full of gas, dust, and bright stars. When we try to look through that disk to the universe beyond, it's like trying to see a distant mountain through a thick fog. The dust blocks the light from the galaxies behind it. For years, we knew something massive was there, but we couldn't get a clear look at it. We just saw its gravitational shadow. With newer telescopes, they can see in infrared and radio wavelengths, which can penetrate the dust. We've started to piece together the picture. The heart of the Great Attractor region appears to be the Norma Cluster, another massive galaxy cluster. But the pull is so strong that it seems to be caused by more than just the Norma Cluster alone. It's likely a huge concentration of many galaxy clusters and the vast filaments of dark matter that connect them all. So our cosmic journey is a long and winding one. The Earth orbits the Sun. The Sun orbits the center of the Milky Way. The Milky Way is moving within the local group, and the entire local group is on a cosmic road trip, flowing at over 600 kilometers per second across the universe, drawn toward the Great Attractor at the heart of Laniakea. We are part of this grand, silent, invisible flow. Laniakea is huge, but the universe is much bigger. Our supercluster is not an island. It's just one part of an even larger structure, the cosmic web. If you could zoom out far enough to see the entire observable universe, it wouldn't look like a uniform soup of galaxies. It would look like a sponge or a neuron network. There are vast, nearly empty regions called voids. These can be hundreds of millions of light years across, with very few galaxies in them. Separating these voids are long, thin strands of galaxies called filaments, and where these filaments meet and intersect, you get the dense, bright knots. These knots are the superclusters. The cosmic web is the true skeleton of the universe, a network of matter and dark matter shaped by gravity over billions of years. Laniakea is one of these intersections in the web. It has neighbors, just like a watershed on Earth is bordered by other watersheds. Laniakea is bordered by other superclusters. The boundary of Laniakea is a surface where the gravitational pull is balanced. On our side, galaxies fall toward the Great Attractor. On the other side, they fall toward something else. One of our nearest neighbors is the Perseus-Pisces supercluster. It's another long, filamentary structure, and we are moving directly away from it. It's like we're on one side of a cosmic mountain range, and Perseus-Pisces is on the other. There's a gravitational divide between us. Another important neighbor is the Shapley supercluster. Shapley is an absolute monster. It is the most massive concentration of galaxies in our local universe, even more massive than the region of the Great Attractor. It's a bit further away, but its gravity is so immense that it is also pulling on us. Some astronomers believe that the overall flow of our region is actually a result of a tug of war. We are being pulled toward the Great Attractor, but the entire Laniakea structure itself is being gently pulled toward the even more massive Shapley supercluster. This highlights how complex these cosmic dynamics are. It's not just one pull, but a delicate balance of many different forces acting over unimaginable distances. The discovery of Laniakea was a huge step, but it also opened up new questions about the even larger structures that might influence our own supercluster. The map is still being drawn. Every new survey of galaxies adds another layer of detail, refining the borders and revealing the flows that connect everything. So, what does the future hold for Laniakea? As we've touched on, its future is one of dissolution. The name Immeasurable Heaven is a beautiful snapshot of the present, but it's not a permanent state. The force of dark energy, this mysterious pressure that is causing space itself to expand at an accelerating rate, is the ultimate winner on these large scales. Over billions of years, this acceleration will stretch the fabric of space-time so much that it will overwhelm the gravitational pull holding Laniakea together. The galaxies and clusters that are now flowing toward the Great Attractor will see their journey slow down, stop, and then reverse. They will begin to accelerate away from us and from each other. The structures that are already gravitationally bound will remain so. The Milky Way and Andromeda will still collide in about 4.5 billion years to form a new, larger galaxy, which some call Milkometa. The galaxies of the local group will stay together. The dense core of the Virgo cluster will likely remain a coherent object. But the larger connections, the gentle gravitational rivers that define Laniakea, will cease to exist. Eventually, the expansion will carry the Virgo cluster away from our local group. It will carry other distant galaxies over a cosmic horizon, a point beyond which their light can never reach us, no matter how long we wait. They will be moving away from us faster than the speed of light, not by traveling through space, but by having the space between us expand that quickly. From the perspective of a resident of our Milkometa galaxy in the far distant future, the universe will look like a very empty place. They will see the local family of galaxies, but beyond that, there will be nothing but darkness. All of the other superclusters, all the 100,000 galaxies of Laniakea will have disappeared from view. The evidence of our grand cosmic home, of the Great Attractor, of the cosmic web, will be gone. Future astronomers in that dark era might conclude incorrectly that their small group of galaxies is the entire universe, just as our ancestors once did. We are lucky to live at a time when we can still see the evidence of these magnificent structures. The discovery of Laniakea changed our perception of our place in the universe. It gave us a new address, a new home, but it also gave us a new understanding of what home even means on a cosmic scale. It's not just about a location, it's about a shared destiny, a shared motion. We are all, the 100,000 galaxies of Laniakea, part of a single, majestic, flowing system. It's a humbling thought. Our planet is a tiny speck orbiting an average star. Our star is one of billions in a large galaxy. Our galaxy is a small player on the edge of an immense supercluster, which itself is just one node in a boundless cosmic web. And the whole thing is a temporary pattern, a beautiful cosmic swirl that will one day fade away. But it's also empowering. We on this tiny speck, have managed to figure this out. Using our ingenuity, our technology, and our relentless curiosity, we have traced the invisible lines of gravity across 500 million light years. We have drawn a map of the immeasurable heavens. We have found our home. And knowing our address, knowing that we are part of this grand, silent dance, makes looking up at the night sky a profoundly different experience. You are not just looking at distant lights, you are looking out from inside a river of galaxies, a part of the great cosmic flow of Laniakea.